So my name is Tomas. I wrote the GLM package, which this talk is going to be about. So I'll first go over introduction to GLM, like the very basics of what it is, and then I'll talk a little bit about penalized GLM. After that, I'll go to talk about HTOS implementation and list of supported features. And then I'll do a small example on a cover type data set, as Arno mentioned. I'll do multinomial classification and then binomial classification. And I'll do some feature engineering using other HTOS features to generate more data to get better model. And then in the end, I'll summarize like the best practices how to use GLM on HTOS. So first, what is generalized linear model? So it's a well-known statistical tool. It's existed for a long, long time. And it fits a linear model to your data. What it means is that you assume that the relationship between the response and the predictors is like a linear combination. Now you can see that the generalized linear model is a little bit more general than that. You have like link of y instead of just y. That means like the response is transformed by a nonlinear function up front, but nevertheless the model is still a linear. Well, there are some advantages with that. It's easy to fit. It's easy to understand and interpret, which is important if you want to know why your model predicts A versus B. And it has well understood statistical properties. Now you can use it for regression problems with Gaussian, Poisson, Gamma, 3D. You can use it for classification, both binomial and multinomial. Binomial is also called logistic regression, which is well known. Now, unlike other models, or like compared to some more complicated models like GBM and deep learning, GLM is a simpler model. It's only a linear model, so you really need to provide good features. It might not work as well on a data set where which is like raw and the features are not as descriptive. So it is parameterized by family and link. Family captures our assumption about the distribution of the response. So example is Poisson for regression on count, or a binomial for logistic regression for two-class classification. And link is a nonlinear transform of the response, which allows us to send our prediction through like exponential function, so that the effects turn out to be multiplicative versus additive, and stuff like that. And it is fitted by maximum likelihood, which means we pick the set of coefficients which give us the highest probability of observing the training data set. And that needs an iterative solver. There's no closed-form solution. So here's a simple example of a simple fit. On the left side, you see, so it's a two-class classification problem. On the left side, you see plain linear regression fit, which fits straight line. Doesn't seem to do that great in this case. Logistic regression on the right, that's way better. Now, why would you penalize your GLM? So, as any other machine learning tool, it can overfit, meaning you get really nice performance on the train, but test performance sucks. And it has a problem with correlated variables. So if your data set has correlated variables, which is quite common, the solution is no longer unique, and it's not quite clear where to put the coefficients between, how to spread them between correlated variables. So adding a regularization solves both of these problems. So adding regularization, it means we put additional term to the problem we are solving. And so we want to maximize the likelihood, but at the same time, keep the norm of the coefficient vector minimal, which is like being more conservative in our assumption. Kind of don't trust really too high correlations. And then there are two common norms we use. It's L1 norm and L2. L1 is also called lasso. L2 is called, L2 regularized regression is called rich regression. They have some interesting differences between them. So the advantage of L1 is that it gives you sparse solution. What it means is if you regularize sufficiently, some of the coefficients will be dropped to 0 and will drop out of the model completely. L2 tends to produce dense solutions, but it's easier to fit. And they also differ in how they handle correlated variables. So the L1 penalty tends to pick one of the correlated variables and drop out the other. L2 penalty will push both coefficients to the same value. So it depends what's the right approach for a data set. And then elastic net combines L1 and L2, which is very useful in some cases. So this is a simple visualization of for L1 penalty and L2. You can see the blue region on the left is a region with where the size of the vector where L1 norm of the vector of coefficients is below certain threshold. On the right, we see a circle, blue circle, which is L2 norm of the coefficient is below certain threshold. And the red ellipsis is our loss function. Is in this case, mean squared. So that's where the mean squared has constant value. And now we see that our solution to this would be where the two meet. And you can see that because on the left, it's a diamond, we are far more likely to hit a point where one of the coefficients is 0. On the right-hand side, it's a circle, so not really, you see, like, we got both non-zeros in this case, while beta 2 would be 0. This is another visualization of the difference between L1 and L2. So what we see here is the regularization path, meaning it's the same problem fitted at different regularization strengths. It goes the strongest on the left to the weakest on the right, and we plot how the coefficient value change. And so we see on the left, we see rich regression, which all the coefficients are having non-zero values, and kind of you can see that some coefficients accelerate, like they're not exactly linear how they change over time. Versus on the right, we have L1 norm, we have lasso, where the coefficients, like it starts empty with no coefficients in the model, and as we start decreasing regularization, the coefficients are entering the model. And as we are moving forward, they change in piecewise linear fashion. So now about H2O's GLM. So our implementation is full distributed and parallel. We handle data sets of up to hundreds of thousands of predictors. It scales linear with a number of rows, meaning the rows are not the limit. If if your data set is too big, you can add nodes and get the same time, or be able to process like twice as large data set. And it has all the standard GLM features. So we have all the standard families. We have support for observation weights, for offset. And we have elastic net regularization with lambda search, which provides efficient way of computing the full regularization path we see on the slide earlier. And we have several solvers for different types of problems. So if your problem is very wide and you want a dense solution, use LBFGS. If you're interested in problem with like fewer predictors, the iterative rebated least squares tends to be the best. We handle categoricals automatically, so you can upload your data set and categoricals will be auto-expanded for you, which is actually more efficient than pre-expanding them before. One note about missing values. You have to handle missing values yourself, so GLM will ignore all rows with at least one missing value on it. As I mentioned before, we have elastic net regularization. It extends the standard GLM by adding a penalty. Penalty in our case is defined similar to as in some other packages like GLMNet. It's defined via lambda and alpha parameters. So lambda is regularization strength, and alpha distributes or controls the distribution between L1 and L2 penalty. If you set alpha to 0, you get no L1 penalty whatsoever, and it's rich regression. If you set alpha to 1, it's lasso, and if anywhere in between, it's you get elastic net. So here's an example on a large data set, which I'm not going to show live, but this is what we ran earlier. So it's a well-known airlines data set. It's 20 years of airlines data, 100 million rows, 31 columns, 12 gigs in the raw CSV, 4 gigs upon loaded into H2O, because H2O compresses the data when it loads it in. And the goal here is to predict when the flights get delayed based on historical data. So we ran this on EC2 cluster with 8 nodes, 64 cores. As you can see, the cores in GLM case, GLM is pretty good at keeping your cores occupied. It scales well, so you can expect the the cluster to get maxed out during computation, and then it got result in about 20 seconds. So now I'm going to switch to the example which I'm going to do today interactively, which is the cover type data set. So the cover type data set tries to predict forest cover type based on cartographic features like elevation. It has 500,000 rows, 55 features, 11 numeric columns, plus 2 categorical, but if you expand them, they come out to 55. The response has 7 classes, so it's a multinomial problem. And because we have 7 classes, the way GLM is fitted for multinomial problems, you get a set of coefficients for each class. So we got actually 385 features to fit in this case. And you can check the tutorial code on the USB drives. So I'm going to switch to RStudio at this point, and I'm going to do the example live. Okay, so the demo, by the way, the demo uses a few convenience functions which you need to execute up front before running anything else, and I'll go over what they do later on. But we start here. So I already have H2O imported, and I think I have Cloud running. So we start by removing all the data from the cloud just to be sure we don't have any garbage around. And now the first thing, we need to import the data. So I'm going to do that. It's pretty fast. Now, Oh, yeah, sure. All right. So we have data in. We're going to be running, data science problem or machine learning. So we want to be sure our model is correct, which usually is done via some sort of a holdout. So I'm going to split my data set into 3 parts, train, test, and validation. Okay, so I have my data set split into 3 parts, and I'm going to run a multinomial problem. Now, I don't have much time, so I'm going to skip the first line. The first line actually gives a model which is no good. I'm going to talk about it in a little bit. So I'll run the second model. So the problem with the first model was that the regularization was set too high, and the resulting model would basically be predicting only the majority class, which essentially is useless. You don't have to be running any model at all. So the second one reduces the regularization from the default. We can inspect the result. So out of this is a multi-class problem. So what I'm really interested in here is the confusion matrix. There's a bunch of other outputs, but I'm not going to go over them right now. So this is my confusion matrix on the test set, where I'm basically interested in my classification error, which is 27%. Predicting only majority class all the time would give me like 51%. So the model, actually is useful. It reduced our uncertainty, but it's not. 27% is still quite high. So maybe we can simplify our model a little bit. Multinomial is a difficult problem, especially for linear models. So maybe we can look only on, if we can find a binomial problem, and we can see that class 1 and class 2 are the 2 majority classes, and there's quite a bit error in deciding between them. So maybe we can simplify our model and just build a classifier to distinguish between class 1 and class 2. So what I'm going to do next, I'm going to filter my data set and take only the rows which are either class 1 or class 2. And then I'm done. I'll set the levels because I only have 2 classes now. And again, I need to do my split. So I'll do that. And now I can run my binomial model. Now, binomial model is way simpler, so I can run with all the defaults, and I'm already done. We can check the performance. Okay, so you can see this is binomial output. It's quite different from the multinomial in the sense that, well, we have some more values which we don't have for multinomial, and our confusion matrix here has like a threshold associated with it. And that's because when predicting two-class problem, we basically get probability for class 1 and probability for class 2. But when we are turning into the classifier, we can pick where to do the cut based on various criteria. So we might have different costs associated with classifying, with missing class 1 versus, missing class 2. So we might want to tune the classifier accordingly. H2O provides various metrics to pick the threshold. These are like commonly picked metrics, how where to put the decision point. But you can basically use your own threshold if you wish. The default for H2O is max F1, which we see here. The threshold is 0.42, so it's not 0.5, and we get 23 classification error overall on at this threshold. Actually, another metric which is commonly used for validating binomial classifier is AUC, which if I would plot all these, and we actually have more the confusion matrices at different thresholds, evaluated at different thresholds, I would get what is called ROC curve. And then if I would take area under the ROC curve, that is AUC, and that's basically universal goodness metric of your classifier. It doesn't tell you how it's going to perform at one particular point, but it gives overall performance, at different decision boundaries. So we got 0.85, which is not bad. And accuracy is 23%, down from 27 for the multinomial case. So we see that the binomial case is like way simpler. But maybe we can do better. So as I said before, GLM is a simpler model. It requires good features. So maybe we can try to add features to improve the quality of the model. Now that gives me back to the convenience functions, which I browsed over before. So we can look at them. So basically, I have two types of functions which generate new features. I have cut column, which will take a numeric column, and it will cut it into intervals, and then the categorical variable with different intervals. And I use H2O hist to build a histogram to come up with the decision with the breaking points of the intervals. And I basically take the bins which have some non-trivial support here at least 1,000 counts. So I'll generate new categorical features for each numeric column I have. And then the second function is interactions, which will generate interactions between categorical columns. Basically, you put two categorical columns, and then you get a new one, which combines the levels of the two. These tend to be useful in general case. This is an example of how to easily improve the performance of your GLM model. And now the convenience function will perform the same operation over all train, test, and validation. But it is important to only evaluate the intervals to find the breaking points only on the train. We don't want to propagate validation data set. Well, we don't want to pollute our validation data set. And then I have the third function just hard codes the features I added for this data set, and that's because I will use it twice. So we can go back here and execute these to get the extra features. Okay, so I'm gonna run the model, and I see that I got an error, and that's because I added significant number of features, and the default solver at this point is no longer able to solve this problem because we are running quite a small instance with not enough RAM. So I can run with LBFGS, and again I'm gonna skip a step which runs with default regularization, which turned out to be too strong in this case. So I'm going to skip a step and evaluate the better model with, again, 1e minus 4. So it shouldn't take too long. All right, so we get extended model. So we can look at how it did. Again, my confusion matrix is for F1 optimal threshold, and we can see that it's 17% or 18% down from 22. So it's a significant improvement. We can also see that AUC is up to 0.9, up from 0.85. So the model did way better than before. But there is still room for improvement. So one thing is, how did I pick the regularization strength to be 1e minus 4? It's kind of arbitrary. And then the other is, I ran with LBFGS solver, well, because I have wide data set now. And I ran with L2 only penalty, and that's because the LBFGS does way better with L2 penalty only. And just to get a quick estimate. But what I added earlier, I added a lot of extra features, and some of them might not be as useful, while some others might be quite useful. So maybe running with L1 penalty would be better. Now, I couldn't run with L1 penalty before. It was complaining because there wasn't enough RAM. But I can run if I run with lambda search. And that's because lambda search is smart, and as he's computing the regularization path, as you saw before, he only has a subset of the coefficients which are actually in the model, and he can filter out the coefficients which are obviously not going to be in the model. So he's able to work only on the subset of the data set and solve the whole regularization path efficiently. So I can actually run it now. And so what's going on now? He's actually building 100 models starting from lambda max, which has like no coefficients in the model, moving down towards smaller and smaller regularization. Now you can see that it's moving pretty fast right now, and it's because there's only a few models, a few coefficients in the model, but it actually slows down quite a bit towards the end when the model gets bigger. I think I'm gonna skip this one for now. You can run it in your examples, but I'll see if I have time to run this in the end. But it slows down towards the end, so it takes quite a bit. The model it obtains is actually again better than what we had with L2, and it uses only half of the predictors of the ones we generated. So what we did, we came up, we fitted multinomial problem, then reduced it to binomial, then improved the binomial solution by adding extra features. And now maybe we can use those extra features to revisit our multinomial problem again and get better performance there as well. So I'm going to do just that. So I'm gonna call basically the same function as I did for binomial. I'm gonna generate the same features for the full data set and run a multinomial problem there. And okay, so the model is building. Okay, was canceled. Did I cancel it by accident? Okay, well, in the meantime, I'm gonna return back to the slides and go over my slide, and then I'm gonna come back to the model, to the R session. So this is a summary of best practices of how to use GLM with H2O. So one important topic is regularization selection. We kind of saw that a bit on the example here. There are many cases when you know which, so there are two things. Decide whether you want L1 or L2 or the combination, and then the regularization strength. In many cases, because you want a sparse solution, either because you have too many features, or that's your requirement that you really want to understand your model, or you assume that you have a lot of noise in the data. In other cases, you don't know, and then that's always the best way is to try both. So what I usually do, I would try L2 only with LBFGS, and then another model with either 0.5 or with alpha either 0.5 or 0.99. Generally, I don't recommend running alpha 1 exactly, because L2 penalty, a little bit of L2 penalty helps. It speeds up the fitting process, and it's more stable fit. Yeah, if you're not sure, try both. Usually, there's no need to do grid search over alpha outside of trying like few values like 0.5, 0.99. Doesn't tend to be too sensitive to alpha. Now, if you have wide data sets, as we saw earlier, you might not be able to use the default solver with the default parameters. So you can either run LBFGS with L2 penalty, or iterative reweighted least squares with L1 penalty and lambda search, which will often run for quite a bit, but you're guaranteed to get the optimal regularization strength, which is a nice property. And also your model will be sparse, which is often benefit. You can also run LBFGS with L1 penalty, but that one doesn't always run fast. It sometimes tends to iterate for a long time. So often when I run with L1 penalty, even on wide data set, I prefer to run lambda search with iterative reweighted least squares over LBFGS. But it depends on the case. OK, so that's it for my slides. And let's get back to our model. OK, so this time we get the model. It actually wasn't canceled. And again, I'm gonna look on the multinomial on the confusion matrix on the test set, and we got 21% error, which is down from 28% error before. So we improved the model again, even in the multinomial case, which is expected because they are really similar models. This is just a extended model of the binomial one. And if we went further, there's a good chance that we could improve the model even more. But to be honest, in this case, for this data set, the 3 methods seem to work the best. So there's that. Well, I can run the lambda search model in the meantime to see if it will finish in time. But I go back to questions.
Does nobody have questions?
Hi. Is there a way to weigh your rows by one or more columns? So for example, in the airlines case, right, like you're looking at 20 years of data, but maybe obviously the airline industry has changed a lot and you want to weigh the factors for the recent time, and you probably want to maybe do like a weighing function or something like that.
Mm-hmm. Yeah, definitely. So we support observation weights. So if you are in R or Python, you just apply observation weights as a vector, and you just tell the model that which of the vectors is observation weights. One thing, it has to be C-binded to the frame. So it has to be part of the frame, and it's because the data is distributed on a cluster. They have to be collocated. So the way to ensure it is that you C-bind it to the data frame.
Anybody else?
Hi. Could you comment some more on why alpha doesn't matter that much? So it's all or nothing or somewhere in between, but not kind of towards the ends?
Right. Well, it's just based on my observation. So, when we got the Elasticsearch, I always like ran grid search over, wide variation of alphas, and then I saw that there is usually not much variation really. There's like big variation between like the two extremes, right? Like you are like close to 1 or close to 0. There's a big difference there. But then whether you are 0.5 or 0.75, it's usually not a big difference. And that's what our advisors told us too. So there's usually only 3 or 4 alpha values to try. Yeah.
So, what is the advantage of using GLM in H2O over native R?
Right. So the native, there's a couple of differences, right? So the H2O GLM has elastic net regularization. I think the native R one, I think it fits plain GLM without regularization, right? But I think the biggest reason is that H2O scales to large data, right? So if you struggle with like fitting your problem into one R session, then you might try H2O's GLM, and it scales like linear with rows. So you can we ran it with 7 terabytes. And it computed a model over 7 terabytes in 3.5 minutes. So, I'd say that's the biggest argument for is the scale.
I know in some of the other R packages, such as Rattle, things like that, you can put the machine learning graphs next to each other so you can see them comparison, see which ones actually are fitting your model differently. Can you do that in H2O? Actually have a graph that shows each of the different machine learning algorithms as a comparison on a single graph?
Right, so we used to have that feature in the older version, and we are working back on bringing it to the new H2O. Yeah.
Last question. Cool. Thank you very much. Nope. Never mind.
Any plans to introduce more traditional variable selection stepwise, forward, backwards?
Well, we've been asked about stepwise. Oh, by you? Was it you? No. Okay, I know that someone on the H2O stream. Okay, yeah. So in some cases, the stepwise might work better. So it's always about the priority. So if we get like enough demand for the stepwise, I wouldn't rule anything out. Sure. If there's big enough demand for stepwise, and that seems to be the priority, we'll add it. And I think it wouldn't be, it would be fairly straightforward. So there's no reason why not.
So I think the feature selection question is a very good one. So we know we have the exhaustive search in our package. Because H2 is based on big data set, I think it's a good idea to have the exhaustive search.
Oh, I'm sorry, I didn't get it. Can you repeat the question?
So we know that we have our package for exhaustive search for feature selection. So is H2O planning to have one?
Well, so you can drive H2 from R. So you can, in theory, you should be able to use the same exhaustive search from R with H2O, right? Just like switch the backends. So I don't see a reason why that wouldn't be possible. But in general, for big data, I don't think the exhaustive search is feasible, right? Because like once you have like many features, you're no longer able to run it. And if you have like very few features, then maybe you're okay with small data sets. So it's not like a priority right now to add exhaustive search. But you can do it yourself from R, and just use H2O as backend, and it will work.
Thank you.
Thanks.